Momentum, mo problems. Baby Einstein.
Thanks for that great introduction, Mr. Martin. So I like to look at momentum as mass in motion here. So what I'm really looking at when I think about momentum is how much do I not want to be hit by an object? Ow. Ow. That was a bigger ow. So momentum is the vector quantity, and we use lowercase p for momentum. Momentum is equal to mass times velocity, and the units are kind of funky. They're kilograms times meters per second because we're taking mass in kilograms times velocity in meters per second. So let's look at what was going on with little ow, medium ow, and big ow. When Mr. Martin, thanks, threw the, let's say the table tennis ball, TTB. He threw the table tennis ball at me. That had a tiny mass, and he threw it at a decent clip there, a decent velocity. Well, because the mass was so small, it had very little momentum because there was not enough mass to really do any damage. However, when he threw the basketball, momentum of the basketball, and I'm not gonna lie, the tennis ball hurt because he drilled me right in the neck. Thanks. But the basketball has a significantly larger mass and threw at about the same velocity, so it carried a lot more momentum. So momentum is really just a thought about, well, how much is the product of its mass times velocity? Something with a lot of mass, I don't want to run into that. Something with a little mass, I'm not worried about as much about that. But what does matter as well is the velocity. Momentum, mass times velocity.
3.
Okay, so we're out here. We have Miss Doherty, we have Mr. Luker, we have Mr. Hausler over there, and we have an egg. What we're gonna do is we're gonna throw the egg into the sheet, and hopefully it doesn't break. You ready? Ta-da!
Good.
All right, so we're still outside in school. We went on a nature walk, as you can see. Mr. Hausler's still here. Mr. Luker's still here. Miss Doherty went inside, she got cold. But what we're gonna do is we're gonna take that same egg and we're gonna throw it against a hard wall. And we're gonna see what happens. You ready? Not ta-da. Oh. Whoa!
Whoa, did you just see that? That's right, Mr. Martin was a Division I college baseball player. So you guys just saw greatness. So what I'd actually like to talk about here is, oh, it's coming back, baby. F equals M times A. You saw the egg thrown into the sheet, didn't break at all. The egg thrown against the hard wall, that did break, and it actually boils all down to force equals mass times acceleration, Newton's second law. I'm gonna do a little rearranging here. So that's still force, and I'm gonna still leave that mass there, but what I am gonna do is use the definition of acceleration and substitute that in. Acceleration, way back when, early on in the year, is change in velocity over change in time. Well, what I'm gonna do is multiply both sides by that change in time. So I'm gonna move that delta t to the other side here, and it's all valid, it's all just math. I'm gonna say force times change in time is equal to mass times change in velocity. What did the sheet do versus what the hard wall did? Well, mass of the egg is the same. Change in velocity, it goes from, I don't know, 100 meters per second, he's got a cannon, to 0. That happens no matter what, if you're hitting the sheet or if you're hitting the wall. But what does change is this impact time. What happens is that sheet slows that egg down over a longer period of time, just like an airbag in your car works. It increases the impact time. So if this quantity goes up right here, if time increases, what has to happen to force? Well, in order to keep that constant over here, that force has to decrease. So we get a whole lot less force as it takes longer and longer to slow that thing down.
Good. All right, so we wanted to show you mathematically the force difference between throwing the egg into the sheet and throwing it onto the wall. First off, let's look at the sheet. Here we have the equation that Mr. Hausler just spelled out for you. Okay? F times delta T equals M times delta V. We have it set up on both sides. Now, we use the same egg, so we're going to say that the mass of the egg is the same. We're going to assume that I threw it at the same velocity. Now, if I threw it at 30 meters per second, in both cases with the sheet and the wall, it had to get to 0 meters per second. So our change of delta V, final minus the initial, is negative 30. So again, this is the same. So like Mr. Hausler said, the only thing that has to change is the time, right? It took a lot longer for the egg to slow down against the sheet than it did against the wall. So if we set this up and we have our force that the sheet applies, we're going to say it's about 1.8 newtons of force this way. If we throw this way, all right, 1.8 newtons of force on the egg from the sheet, okay? Now, for the wall, since the time was much, much less, we said that's approximately 22.5 newtons of force on the egg. Obviously, much, much more, and that's what caused the egg to break.
This quantity on the left and this quantity on the right, we already talked about F delta T equals M delta V. Well, this quantity on the right-hand side is commonly known as commonly known as change in momentum, because it's mass times change in velocity. It tells you how much momentum starts and ends. But the big thing is this F delta T quantity over here is known as impulse. And if you think of impulse, something's hitting something else. It's hitting it with a force for a certain period of time. Another big thing, and a term you will hear used a lot, is impulse and change in momentum. Be aware as well, because it's newtons in force, time and seconds, that units for impulse can be Newton times second, or that's also equal to the same unit for momentum, kilogram times meter per second. Woo!
The MA is strong with this one.